We've already developed maximum and minimum functions for particular worded problems, but this time around what we're going to do is use calculus to actually help us to find maximums and minimums. So here's a classic problem. A loop of string length 100 centimeters is to be formed into a rectangle. Find the maximum area of this rectangle. So here's our rectangle, and we've got x, x, y, y. Now I know that 2x plus 2y equals 100. Okay, so the perimeter is 100. Now you might remember that what we were doing is then we want to get the maximum area. So the area is the length times the width, or x times y. We want to get this in terms of just one variable only. So typically what I do is I try to let the variable be x. It can be y, that doesn't really matter, but I'm going to say that 2y equals 100, take away 2x. Y is equal to 50, take away x. I've divided both sides by 2. So instead of using y, what we can use is 50 take away x and 50 take away x. So I'm going to get my area now and write it, instead of x times y, write it as x times 50 take x. Now what this is an area function. And what it describes is how the area changes based on the value of x. Let's just see if we can imagine it. So when x is 0, we can see via the null factor law that we're going to get 0. So when a of x equals 0, or let's say when the area is equal to 0, we get 0 and we get 50. And we know that this is a parabola. If you expand it out, you'll see that we've got 50x take away x squared. So it's an inverted parabola. So it's going to go up like this, right? And here is our maximum area. So what this graph describes basically is how the area changes based on the value of x that you choose, okay? And we know for parabolas that the middle of these two x-intercepts will be where the maximum occurs, okay? So what we would have done previously is banged in 25 into my area function, just done a of 25, and that'll tell us that it is 25 times 25. Should know this. 10, 12, 0, 2 2s are 4, 5, 2, 525 centimeters squared. So that's the maximum area we can produce when x is equal to 25. Now you might be going, yeah, well, so what's the big deal? Like, why is this in calculus then? Well, what we can also do is once we've got this function, this area function, what we can do is use calculus to hunt for the stationary points. Okay, so we know that this is going to be a stationary point. So I'm going to rewrite a of x as this form here, which is 50x take away x squared. And what I'm going to do is get my gradient function. I'm going to call the gradient function a dash x equals 50 take away 2x. Now what I'm going to do is go, hey, gradient function, when do you have a gradient of 0, i.e., when is your stationary point, or when does it occur? When we solve for x, surprise, surprise, it says I've got a stationary point at x equals 25. Now we know that, okay? So I'm not denying that calculus is doing something that we already know, but it's just nice to see that calculus knows where the 0 gradient point is. Right, and then what we would do is a of 25, same deal here. Once we find out that that's where the stationary point occurs, pop it in there and we get 525 centimeters squared. So we can do this via calculus, or we can not do it via calculus. It doesn't really matter. Now you'll note that this technique can be done with quadratics, so we can not use calculus with quadratics. But if we actually get a cubic function, which we'll see later on, and we want to get a maximum of a cubic, we actually need calculus for that because the maximum doesn't occur at the midpoint of the x-intercepts. It occurs somewhere else, around the midpoint, but not actually at the midpoint. So we need calculus to actually tell us where that's going to occur. But more on that later. Okay, so here's another problem. The sum of two positive numbers is 26. Find the numbers such that their product is a maximum. Okay, so again, this is one that we could do without calculus, but we're going to use some calculus for it. So the sum of two positive numbers is 26. All right, so the sum of two positive numbers is 26. Okay, so what we're doing is we're attempting to maximize the product. So x times y equals, let's just call this the maximum. All right, so again, my maximizing function has two variables in it. To use calculus or to model this via a function, I need one variable only. So I'm going to go up to this original piece of information and write this as y is actually 26, take away x. Right, m equals 26 take away x times x. So all I've done is I've substituted that value for y into there. All right, so here's my maximizing function. So we want to get the maximum value there. So I'm going to go m of x, because it's in terms of x only, is equal to 26 take away x multiplied by x. Right, again, because this is quadratic, I know that one of them is 0 and one of them is 26. It's going to be 13. So the value of x that does this is going to be 13. But I'm going to pretend that I'm going to use calculus on it. All right, so I'm going to pretend I don't know that this is a technique, and the only technique I know is calculus. So I'm going to expand that because we can't derive that yet. M dash x, the gradient function, is 26 take away 2x. Can you please find where the stationary points are, i.e. can you find 0 gradient points? And it goes, yep, for sure. There's one at x equals 13. All right, so I know that there's one at 13, and then all we do is find the numbers such that their product is a maximum. Okay, so number 1 is 13, and number 2 you can see is also 13. Okay, so the two numbers are 13, i.e. It's a square, okay, or a square number. So you can find out what their maximum is going to be. It doesn't ask for that, it says find the numbers such that their product is a maximum, but let's just get the maximum anyway. It's going to be 13 by 13, which is, I think it's 169. Let's check that. Yeah. So there we go, using calculus again, but could use that other technique. All right. An open box is formed from a piece of metal. Okay, now noting that we've got a box here, boxes look like this, which is length, width, and height, width pointing to this thing here, which means that generally what we get out of these ones here is a cubic function. So actually, this time around, we've got no choice but to use calculus to find the maximum. All right, so what we've got here is an open box. So let's just draw the original. It's a 40 by 20 open box. And the way we form open boxes is we chop out the edges here. You might have done this activity. We chop out the edges here and we fold them up. So it's going to be x, 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 all the way through there. So we cut the same square out of each side and fold it up to create our open box. So looking at what that's going to look like in terms of a box, what we're going to get is this side here is going to be 40, remove the x and the x, so it's 40 take 2x. This side here is going to be 20 take 2x, and the height, well, that's going to be x. All right, so state the dimensions of the box in terms of x. So we've got a length, let's do A, width, and height. So the length, we're going to say is 40 take 2x. The width, and that's meters. The width is going to be 20 take 2x meters. and the height is going to be x meters. Okay, state the domain. I don't know. What I want to do is get a function first, picture the volume function, okay, and then go from there to work out the maximum volume of the box. So this I would do before question B. So let's do C first. Using calculus, determine the maximum volume of the box. So volume is length times width times height. Volume, v of x, my volume function, is going to be these three multiplied together. So it's going to be x, 40 take 2x, and 20 take 2x. All right, so now that I've got my volume function, I can quickly see what the graph is going to look like. So it's going to be 0. That's one x-intercept. This x-intercept is going to be negative 20 or negative 40 on 2 is 20. And this one here is going to be 10. All right, I'm going to just improve my diagram a little bit. So 10 and 20. Now the cubic is going to be a positive cubic. So what happens is it's going to come up like this, go down, and then back up there. All right, so I can see here that this is v of x, my volume, with respect to x. And what I can see is it produces positive values between 0 and 10. So I'm going to say that x is an element between 0 and 10. Now, it also looks like it produces volumes that are greater than 20 for x when x is larger than 20. So this seems weird because it says it produces negative volumes here, and then it kicks back, and it actually looks like I can create volumes that tend towards positive infinity, which seems weird because how could you get a box that holds infinity stuff? Well, this is a good example of why humans are required. Because what we see here is if x is larger than 20, let's have a look at what happens to these side lengths. Right? X, this one here, for sure, can be larger than 20. But if this x goes larger than 20, let's look at, say, 25. Negative 2 times 25 is negative 50. 20 times negative, 20 take away negative 50 means that this side length is negative. And it's the same thing with this side length here. This will be negative. Now what happens is the negative times a positive produces a positive answer. So what looks to be an acceptable or positive volume actually is unacceptable, because to get that volume you need to make two side lengths that are negative, which is not possible. So we're going to stick with our domain of x as an element between 0 and 10, not inclusive of the endpoints because they don't create a box. Okay, again, there's some circles where it can be argued that you would include the endpoints, but that discussion is for a later time. Okay, so what we've got is we've done state the domain. Now using calculus determine the maximum volume of the box. Now you might think, oh, isn't it just going to occur at 5? No, all right, because this is a cubic function, okay, and cubics don't have maximums at the midpoint. So we must use calculus on this. So let's look at our v of x function. And what we've got to get is a derivative for this. Now, unfortunately, that does mean that I've got to expand this out to become single term and then derive it. So 2 4s are 800. Take away 80x. Take away 40x plus 4x squared. All right, let's clean that up a little bit. Notice I'm not going to the derivative just yet. 4x squared, take away 120x plus 800. Still not ready to derive. I've got to get it to all single terms. 120x squared plus 800x. All right, now that it's at single terms, I'm going to go v dash x equals. All right, that's 12x squared, take away 240x plus 800. Alrighty. Now what we want to do is hunt for zero gradient points. Okay, just halve all of them. Does 6 go into 400? Don't think it does. Let's halve it again. 60x plus 200. All right. So what I've got to do is factorise this thing here. It probably does factorise reasonably well, but anyway, let's just give it a go. 3x, x, and okay, so I'm going to cheat a little bit on this one and get the calc to factor this thing for me. Okay, so recall that factor is in transform, factor, it might be a quadratic formula. Take 60x plus 200. Okay, so it is quad formula. So what we're going to do is solve this thing here. All right, lucky I didn't persist with that for too long. So 0 equals x equals plus or minus 10 root 3 on 3 plus 10. All right, so what we've got two stationary points, and that makes sense. We've got one here and one here. So calculus has gone and found two of them for us. Well, which one do we take? Well, it's got to be this one here, and I know it's going to be somewhere near 5. So one of them is going to be near 5. It's going to be the negative one. So let's see how close it is to 5. So let's go and decimal approximate that, and it should be somewhere near 5. Yeah, it's 4.2. All right. So we're going to say, but x is an element as we've established between 0 and 10. So x is equal to 10 root 3 on 3 plus 10. Alrighty, so using calculus determine the maximum volume of the box. Alright, so this is where the maximum occurs at this value here. Now what we're going to have to do is v of 10 root 3 on 3 plus 10. So what we're going to do is say, I know your maximum occurs here, and now what is your maximum volume? So we shove that into the original function. Now, the original function is x times 40 take 2x times 20 take 2x. So we go f of that thing there, and let's just see what the exact value looks like. That's it. We hit simp on that. It does give us the rather nice 800, or 8,000 rather, root 3 on 9. What are we in? Meters cubed. Okay, so that's going to be the best configuration of the box to produce this. So this last question is a bit of a trick question. So the fact that they use the word maximum surface area seems to suggest that you're maximizing surface area, or that you need some calculus to do this question here, but in fact you don't. So what we're going to do is part D. Now we know that x equals 10 root 3 on 3 plus 10 is where the maximum volume occurs. So what we're going to do is use that value there to actually find out what the surface area is going to be painted. So it's only the outside of the box. So it's going to involve us painting this, so two of them to get the back and that, and then the underneath. So we're going to write out our surface area formula. So surface area, let's go call it S of x, is equal to, so we've got two lots of 2 lots of the width, so that's 20 take away 2x, times x. So we've got 2 lots of them, plus 2 lots of the other one, which is 40, take away 2x times x. Put some brackets in there. Right, so it's 2 lots of them, 2 lots of them, and then we've got only one bottom. So that's going to be plus 40 take 2x times 20 take 2x. So that's our surface area function, and we know that the maximum, we're going to use this value of x to create our shape because it's the maximum volume that we want, and that'll give us the maximum surface area. So S of 10 root 3 on 3 plus 10 equals, and what you would do is I would type in the formula, so it's going to be 2 times 20 take 2x times x plus 2 times 40 take 2x times x. Let's just see, do I have enough brackets? Can never get enough brackets. Plus 40 take 2x times 20 take 2x. And we're going to say, can you do that with the value of x that maximizes the volume of my box? X equals. Alright, so that basically puts the value of x that maximizes the volume into the surface area, which tells us that, which if we hit simp on that, says that our maximum surface area is 800 bracket root 3 plus 1 on 3 meters squared, because surface area is an area. Alrighty, beware. Calculus can be used to find a local maximum or minimum, but these are often not the actual maximum and minimum values of the function. All right, so let's just see an example here. So here we've got a function here, and it says find the maximum and minimum values of the function. So what students tend to do is fall in love with calculus and then use it all the time to find anything that involves a maximum or a minimum. And I'll show you why to beware. Okay, so if I go f dash x, because I want to get the maximum and minimum, I'm going to go 3x squared as the derivative of f dash. 0 equals 3x squared. X equals 0. All right, and it seems to suggest that the maximum occurs, or the minimum occurs, at x is equal to 0. Y is equal to 2. All right, but let's have a think about this in practical terms. This is just the standard cubic function up 2 units. So here's 2, goes like this. Negative 2 is over here, produces that value there. 1 is over here, produces this value here. So in this case, what calculus has done is found the 0 gradient point, okay, which is a stationary point, but by no means the largest and smallest value. So the largest and smallest value is actually obtained by the endpoints. So f of negative 2 equals negative 8 plus 2 is negative 6. That's the min value. And f of 1 is equal to 3, which is the max value. All right, so this seemingly easy problem does trip students up, because once you know calculus, every time you use or you see these words here, you tend to use calculus on them. And I don't know, I suppose you've got to think about it and say, well, I'm only going to use calculus on the things that need calculus. Okay, so we've got a canvas shelter is made up with a back, 2 square sides and a top. We know that the area of canvas available is 24 meters squared, and we want to get the volume enclosed by the shelter. So find the dimensions of the shelter that will create the largest possible volume. So what we're going to do is maximize a volume function. So we know that volume is going to be x times y will give us the amount of space we've got inside this thing. And we know that the area to make this canvas is 24 meters squared. So what we're going to do is just get the area that's required. So that's this, 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 and this. So what we've got is area is x squared, that's that bit. This bit's the same, x squared. This back bit is x times y, and the top bit is x times y. And I know that the area I've got available is 24, so I'm going to go 24 equals 2x squared plus 2xy. And what I want to do is make this volume function, v of x, with x times x, which is x squared, and then y. I'm going to get y in terms of x over here. So what I'll do is go 2xy equals 24, take away 2x squared. Y is equal to 24 over 2x, take away 2x squared over 2x, one of them, that, and 12. So y is equal to 12, take away 12 over x, thanks, take away x. So it's going to be 12 over x, take away x. All right, so find the dimensions of the shelter that will create the largest possible enclosed volume. So I'm going to go v of x equals x squared, 12 over x, take away x cubed, that, v of x equals 12x, take away x cubed. All right, so we've got our volume function, and what the best thing to do is to try and picture what this might look like. So sketch the graph of v against x for a suitable domain. So we'll draw a quick Cartesian plane, and then what we'll do is we'll get our x-intercepts. So we know we're going to get one at 0, so it's going to go through the origin, because when v of x equals 0, goes through the origin, and we're going to get two other x-intercepts there as a result of doing this one here. Now I'm not too sure what they are going to be just yet. Let's do, actually I can get it, so v of x equals x, 12 take away x squared, x equals 0, and x equals negative positive root 12 equals 2 root 3 plus or minus. So we're going to get one at 2 root 3 and one at negative 2 root 3. All right, it's a negative cubic, so we're going to go like this. All right, and what we can note is that our domain is only going to include these values here, right? So these ones here aren't important to us, because remember, this is the graph of v of x, vx. So what we only want is positive volumes, right? So it's these ones here that we're interested in. So I'm just going to blot out the ones that aren't relevant. So bear with me. These ones here, and we've got our domain. All right, so going back to this problem now, what we need to do is the question, find the dimensions of the shelter that will create the largest possible enclosed volume. So the largest possible enclosed volume is going to occur at this value here. What's that value going to be? We're going to get calculus to tell us what the stationary point is. So we're going to go v dash x equals 12, take away 3x squared, 0 equals 12, take away 3x squared. That is x squared equals 4, x equals plus or minus 2. So it's got stationary points at x equals 2 and x equals negative 2. Now the one we're interested in is the positive 2. Okay, so we're going to say but x greater than 0, so x equals 2. Alright, so the dimensions that are going to create the largest possible volume is going to be width 2, length 2, and height is going to be, that should actually be the length. So I'm just going to go height is 2 and length, I'm just going to rub that out. Now the length is found by doing or finding y. So we know that y was 12 on x plus x, or take away x. I think it was take away x. Let's have a quick look. Y was 12 on x take away x, yep. So if we put this dimension for x, 2 in, that's 12 on 2 is 6. 6 take 2 is 4. All right, and we can see that the maximum volume is going to be 2 metres, 4 metres by 2 metres, which is going to be 4 2s are 8, 16. Okay, so it doesn't ask for the actual maximum volume, but I know that the dimensions 2, 4 and 2 will create the maximum volume. Okay, so find the values of x and y for which the volume is 10. Right, so this one here, we've got this volume function v of x, and we want to find out when it's 10. So we want to find out the values of x and y that make this happen. So let's define our volume function, which it was, this is probably the best form to define it in, 12x take away x cubed. Okay, and what we want to do is solve f of x equals 10 for x. Now it's given us 3 solutions, which does make sense, because if this is our graph here, we're going to get a 10 volume here, a 10 volume here, and a 10 volume somewhere over here in a part that's not relevant. So we're going to say we're going to hunt for equals 10 where x greater than 0, x is equal to the first one, we're going to go 0.89. We're going to assume 2 dp, even though it hasn't said it. Why can I assume? Well, let's have a look at the exact answer. There's the exact answer. Pretty gross. All right, so we're going to assume that VCAR would tell us to do an approximation on this one. So 0.89 is one of them, and 2.9 is the other. Now, recall that y is equal to 12 on x take x. So all I would do now is do 12 over this value of x, take away this value of x. Come on. Here we go. Which is y equals 12.55, and the other one, we'll just grab 2.9. I'm just going to copy that, paste it a bit in there. It's a bit fiddly, isn't it? Paste that there, and I get 1.16. Let me just quickly check that out to make sure that that will produce our value around about 10. So it's length by width by height, 0.89 times 0.89 times 12.55. Now, because of rounding, this is not going to be exactly 10, but it should be pretty close. There it is, very close. All right, if the height of the shelter must be at most 1.7 metres, what will the maximum volume of the tent be? So that means x is equal to 1.7. And so therefore, all we'll do is v of 1.7, we'll put that into f of x on the calculator. So f of 1.7 is, that's the maximum volume we're going to get, is 15.487 meters cubed. That's the best we're going to get if I'm allowed 1.7. Okay, so there you go. There's some applied problems, and the homework will be 18E 1 to 16. So lots and lots of practice of maximising and minimising.